In our prior sections, we were graphing rational functions, but now in 5.3, we're going to solve equations and inequalities with rational functions, and then just look at a type of application problem. We're going to revisit variations. So let's first solve rational equations. I am going to find my LCD and then I'm going to clear my fractions in my equation because that's what I prefer to do. If you prefer to work with fractions and then just build up all of your fractions so they have the same denominator and solve that way, that will also work, but you may end up with some really long expressions. First of all, you always want to make sure that the solutions you get don't give you an undefined denominator, because remember, we're solving equations with fractions. And if you have a variable in the denominator of a fraction, it is possible that you could get 0 in the denominator. First thing I'm going to do is I'm going to make sure that all my denominators are factored. The negative 2 over x squared plus 2x on the right can factor into x times x plus 2. So when I find my LCD, my least common denominator, I look at all my denominators. So I have an x minus 2, and then x times x plus 2. And I figure out what denominator I need that will be common to all three. So that would be x plus 2, x minus 2. And then before I go any further, I want to note that if x is equal to 2 over x minus 2, that will be undefined. I'll get 0 in the denominator. So before I go further, I'm going to write down the values that I cannot use for solutions because they'll give me 0 in my denominators. So x equal to 2, 0, and negative 2. All of those will give me undefined denominators, so I can't use them. So I'm going to solve by clearing my fractions. Now, typically I would multiply both sides of the equation by the LCD and reduce, but I'm going to do a shortcut. If you look at this first denominator here, the x minus 2, what's missing from the LCD is the factor x and the x plus 2. So all I really have to do is take the 2 in the numerator and then multiply by what's missing, which would be the x and the x plus 2. And then I have a minus 1 over x. Looking at the denominator x, what's missing from the LCD is the x plus 2, x minus 2. So that's what I'm going to multiply the 1 by, x plus 2, x minus 2. Equal to, now don't forget there's a negative here in front of this fraction bar, so I'm going to move that up and write this as negative 2. Looking at that denominator, what's missing, and I'm looking at the factored form, the x plus 2, what's missing is x minus 2. Now that I've cleared my fractions, I'm going to go ahead and simplify. So I get 2x squared plus 4x minus 1 times the x plus 2x minus 2 will turn into x squared minus 4 equal to negative 2x plus 4. I get 2x squared plus 4x minus x squared plus 4 equal to negative 2x plus 4. And then on the left, that becomes x squared plus 4x plus 4. And on the right, the minus 2x plus 4. I'm going to move that all over to the left-hand side. So if I add 2x, this becomes x squared plus 6x. And if I minus 4, I just get that that's equal to 0. So now all I have to do is factor, if possible. And this is possible for this case. And set each factor equal to 0 to give me x equal to 0 x plus 6 equal to 0 will give me x equal to negative 6. However, I can't use 0. So don't forget to check your solutions to see if they'll work. And when I say work, I mean so that they don't give you a 0 in any of your denominators. X equal to negative 6 is my only solution, and I could put negative 6 back into my original equation. I think if you do, you'll get like negative 1 over 12 is equal to negative 1 over 12, which is true, so it works. Or we could write this as a set negative 6. In part B, notice that this looks like a quadratic equation. You could try a substitution on the x to the negative 1. If y is equal to x to the negative 1, then y squared could be x to the negative 2, see if it factors. However, I'm going to use the techniques in this section. What I'm going to do is change those negative exponents to positive. So the x to the negative 2 becomes 1 over x squared minus, this is going to be 5. So remember, the 5 stays. The negative 1 exponent is only to the x, so it's 5 over x minus 36 equal to 0. I'm going to find my LCD. So you could write all of these as fractions by putting the 36 over 1, 0 over the 1. So when you look at all of the denominators, the LCD is simply x squared. Also note that x cannot be equal to 0. If x is equal to 0, then two of my terms will have 0 in the denominators and be undefined. So if I'm using the method of clearing fractions, I would look at the 1 over x squared and look at the numerator 1. What is missing from the denominator? Nothing, so it stays, minus 5. What is missing from the denominator is an x, minus 36. What's missing from the denominator is the x squared, equal to 0. What's missing in the denominator is x squared, but 0 times x squared is still 0. And now I have a quadratic equation. I'm going to write this with the x squared first, and then minus the 5x plus 1. At this point, you could use quadratic formula or you could factor. I don't like all those negatives, so I am going to first multiply through by a negative 1 to get 36x squared plus 5x minus 1 equal to 0. So I believe this will factor as 9x minus 1, 4x plus 1. Let me double check. 9x minus 4x gives me a positive 5x. The 9 times 4 gives me the 36x squared. And negative 1 times positive 1 gives me negative 1. So yes, it does work. Setting each of these factors equal to 0 and solving, I should get a add 1 divide by 9. I get x is equal to positive 1 over 9. And I have x is equal to minus 1 divided by 4. So negative 1/4. Neither of those are 0. So both of these are good solutions. And you can actually put them back into the original equation to see if they work. And they both work. Or in set notation, it would be 1/9, comma negative 1/4. Now we're going to move on to solving inequalities. Inequalities, you really have to be careful because remember, if we multiply or divide by a negative, we have to flip the sign. And because of that, it's very, very, very important that you do not divide or multiply by expressions that have variables in them. So do not multiply or divide if there's a variable, because you don't know that the variable stands for a negative or a positive number. You don't know if you have to flip the inequality. So because of that, we're going to follow these steps. We're going to first set the inequality to 0. So we're going to move everything to one side, 0 on the other. And then on the side that has our rational expressions, we're going to combine them into one fraction. So what that means is we're only working on one side of the inequality. The other side is going to be 0. So we are not clearing fractions ever. what we're doing is building up and combining into one fraction. Make sure your numerator and denominator are factored. And then what we're going to use is we're going to use these factors to find our intervals. So we're going to do what we did in a prior section. We're going to set each fraction to, or each factor to 0. We're going to find those points that are going to break up our number line. And then we're going to get intervals between those points. We're going to check those intervals to see where we have solutions and where we have no solutions. Something we have to do is we also have to make sure we check our endpoints to see if they can be included in our solutions. And then, as before, what we're going to do is just get test points in each interval and see if they make the inequality true or false. But the key here is that we're working on one side. If we look at this first example here, 2 minus x over x squared plus 5x less than or equal to 0. Well, that is already set to 0 on one side. So I don't have to do anything. All I have to do on the left-hand side is make sure it's all factored. The numerator is okay. It's just 2 minus x. Oops, pen's not working. But the denominator, if I factor out an x, in parentheses, I'll have x plus 5. Less than or equal to 0. And now I'm setting numerator and denominator, all factors, top and bottom, equal to 0. In the numerator, x equal to 2. Denominator, I have x equal to 0. And x equal to negative 5. Those are the values that are going to break up my number line. So let me go ahead and off to the right here, let me just sketch a number line. And I'll put those values as they appear on the number line, so negative 5, 0, and 2. The test points. Before I do that, I have to check endpoints. So let's look at this. We have x is equal to 2. If x is equal to 2, what's going to happen is that the numerator is going to be 0, and the denominator is going to be 4 plus 10, so it's going to be 14. So I'm going to have 0 less than or equal to 0, and that's true. So I can use 2. I'm going to put a solid dot where 2 is. If we look at x is equal to 0, the problem there is that I'm going to end up with 0 in my denominator. I'm going to end up with 2 over 0, which cannot happen. So I cannot use x is equal to 0. I'm going to put an open circle at 0. And then if you put in negative 5, again, that's going to make the denominator 0. So we can't use negative 5 either. So check your endpoints to see which ones can be part of your solution and which ones cannot. And then we'll go ahead and get ourselves some test points. First, let me sketch my intervals. I have negative infinity to negative 5 with a parenthesis, negative 5 to 0, parenthesis 0 to 2. Now again, remember I differ from the book. I like to put the bracket up to remind myself that when I do write my solutions to include that. And then we can include 2, so bracket 2 to positive infinity. So these are going to be my intervals where I'm going to have solutions or not have solutions. Some test points. Let's see, negative 5, something less than negative 5, maybe negative 6. Between negative 5 and 0, negative 1 seems reasonable. 0 to 2, 1, 2, and greater, I'll use 3. So I'm going to put those test points into my original inequality. Now notice you can also put those 10 test points into the factored form, and that might be easier with the math, but if you made some math errors while you're factoring, you might not catch them. So it's usually best to put it into the original inequality. Now when I put negative 6 into the inequality, I get 2 minus a negative 6 in the numerator, so that would give me a positive 8 over 36 minus 30 would give me a positive 6. So the question is, oops, this is an 8. This looks weird. I'm not going to reduce it. 8 over 6, is that less than or equal to 0? No, because 8 over 6 is positive. It's actually greater than 0. So I can't use anything in that first interval. So let's go to the negative 1. 2 minus a negative 1 would give me a positive 3. And then in the denominator, I would have 1 minus 5, so that would be a negative 4. Is negative 3/4 less than or equal to 0? Yeah, it is. So I can use any x value from negative 5 to 0, and it'll make that inequality true. Let's see, what about 1? If I put in 1, 2 minus 1 is 1 over 1 plus 5 is 6. Is that less than or equal to 0? And the answer is no. Can't use anything from 0 to 2. And then in our last interval, we have 3. 2 minus 3 is going to be a negative 1 over 9 plus 15, so that's 24. Negative 1 over 24, is that less than or equal to 0? Yes. I can use anything greater than 2, and actually 2 as well. So my solution will be negative 5 to 0 with parentheses, union, bracket, 2 to positive infinity. All right, let's do another one. In B, again, you cannot just multiply and clear fractions by the x minus 2, x minus 1, because you don't know if those expressions are going to be negative or positive. You don't know if you have to flip the inequality. So the strategy is to get everything to the one side and have 0 on the right-hand side. So I'm going to minus 3 over x minus 1 from both sides. So this becomes 2 over x minus 2 minus 3 over x minus 1 greater than 0. So now I have 0 on one side. I have to combine these into one fraction on the left. So remember, not clearing fractions, building up so they have the same denominator. And the denominator that we're going to use is going to be x minus 2, x minus 1. So I need to multiply that first expression by x minus 1 over x minus 1. The second, I'm going to have to multiply by x minus 2 over x minus 2. And that's greater than 0. So don't cancel at this point. A lot of times students will look at that and go, hey, I can cancel the x minus 1 and the x minus 2. No, the point is to build them up so they have the same denominator. Don't cancel. Combine in the numerator. This is going to be 2x minus 2 minus 3x plus 6. Don't forget to distribute that negative over the common denominator, x minus 2, x minus 1, and that's strictly greater than 0. Now we have to make sure everything's factored after we get it to one fraction. The denominator's already factored. I just have to simplify the numerator to be a negative x plus 4. Or you can write it as 4 minus x, either way. So we have to find those x values that give each one of these factors 0. In the numerator, if I use x equal to 4, that will be 0. X minus 2 if x is equal to 2. X minus 1 if x is equal to 1. So 4, 2, and 1, those are the values that we're going to use to break up our number line in the order that they appear, which would be 1, 2, and 4. So we have to test the endpoints, 1, 2, 4, before we write down our intervals. Notice that this is strictly greater than 0. So if I put in 4, I will have 0 on the right-hand side, or on the left-hand side, sorry. but 0 is not greater than 0. So I can't use 4. And then 2 and 1 will give me an undefined denominator, so I can't use those. And in general, whenever you have strictly greater than or strictly less than, you cannot use these values. They will not work. So open circle 1, oh, I want blue. 1, 2, and 4. Let's go ahead and choose, oh, sorry, let me write down my interval. So negative infinity to 1, parenthesis, parenthesis 1 to 2, parenthesis 2 to 4, parenthesis 4 to infinity. Test point, something less than 1, 0 is nice. Between 1 and 2, I'm going to write it as the decimal 1.5 because we can always just plug that in a calculator. You could also put 3 halves, but I don't want to work with fractions. And then between 2 and 4, 3 seems reasonable. Greater than 4, 5. If I put 0 into my inequality, and I'm putting it into the original inequality, so let's go look back at that. If you put 0 in for x, you'll get 2 over negative 2, which would give you a negative 1. Is that greater than if you put in 0 for x, you get a negative 3? So is negative 1 greater than negative 3? Yes, it is. So I can use anything from negative infinity to positive 1. If I put in 1.5, I'll get 2 over 1.5 minus 2 is a negative 0.5. So it's going to be 2 over a negative 0.5. And I'm not going to figure out what that is unless I have to. 1.5 minus 1 would be 3 over a positive 0.5. So again, you can put this in a calculator, but what this is saying is a negative number is greater than a positive number, which is false. Can't use anything from 1 to 2. 2 to 4, I chose 3 as a test point. If I put in 3, I'll have 2 over 1. So that would give me 2. Is that greater than 3 over 2? Yes, because 3 over 2 is 1.5. I can use anything between 2 and 4. Greater than 4, I chose 5 as a test point. That would give me 2 over, maybe 6 would have been nicer. Anyway, that'll give me 2 over 3. Is that greater than 3 over 4? It is. If you put 2/3 into a calculator, it's about 0.7. If you put in 3/4 into a calculator, it's about 0.8. Or you can look at it as 0.67 and 0.75. Which means you cannot use anything in here because you'll have 2/3 is not greater than 3/4. It's false. My solution will be negative infinity to 1, parenthesis, union, parenthesis, 2 to 4. And this is not a very long section. Since a lot of the algebra we've looked at in previous sections. So it's just solving equations, solving inequalities. And then this last thing that we're going to look at is some word problems. In particular, what we're going to do is we're going to go back to our variations. And I don't know if you recall the direct variations. That was in section 1.6. The idea here is that when we're working with variation, solve the constant k and then use that k value to solve your problem. So recall our direct variation, that would be y equal to kx. So remember y and x, they can vary, they're variables, but k is not. K is a constant number that does not change. That's why we can solve for k and keep using it over and over again. It doesn't change. So some of the language you'll see if it's a direct variation would be maybe varies directly or directly proportional. We also have an inverse variation. Inverse variation is going to be y equal to, and this time we're going to have our k over our x. So it's inverted. In your book, they will write y equal to k over x to some power. But that's not necessary. K over x is fine. Varies inversely proportional. That would be some language that you may read, and that will tell you it's an inverse variation. And there's also what we call a joint variation, and that would be if you have three variables. So in this case, we have some z value. It's going to vary jointly, meaning you still have only one k value, always only one k. It doesn't matter how many variations are in there, it's always one k. But jointly means two or more variables. So z is going to vary jointly with both x and y. So you may see varies jointly, jointly proportional in the language. Again, your book is going to have z equal to k, x to the n, y to the m. They put powers in there, which I actually don't agree with, because it is possible. It sort of implies that your x and y values are going to have whole numbers for exponents or integers for exponents. But it doesn't take into consideration if you have a variation that has like a root. Regardless, we're going to look at three examples. In example 3, we have the intensity of light, I, is inversely proportional. So I notice that right away, to the second power of the distance d between the observer and the light source. Okay, so all this is saying is that if there is a light source, the closer you are, the brighter the illumination or intensity. The further away you are, the lower the intensity. So the intensity is how much light you experience when you're a certain distance away from a light source. And we're going to call that I. So the first thing I'm going to do is, in that first sentence, that gives me my formula. It's an inverse variation, and the intensity I is, that's my equal, so I know that the intensity I is inversely proportional, so I know I'm going to have my k and then something below it. So what it's inversely proportional to is the second power of the distance d. So that's d to the second power. I have my formula for intensity. The second part of this gives me information so that I can solve for my k value. It says at a distance of 3 meters, so that's when d is equal to 3, a 100-watt light bulb produces an intensity, so the intensity is your I, of 0.9 watts per square meter. So let's stop and think about what we have. We don't know what k is, but we know our distance is 3 meters. So that's going to be 3 squared, because we're squaring our distance. And the 100-watt light bulb, that's just information. It doesn't go into your formula. What goes into your formula is, remember the intensity, our I? It's 0.9. So the first thing to do is solve for k. If you multiply both sides by 9, you'll get 0.9 times 9. That will be your k value. So putting that in your calculator, you should get 8.1. Once we have our k value, we can rewrite our formula as I equal to 8.1. That's constant and it will never change, no matter the distance that we are from our light source. Once we've solved for k, we can answer the question given to us, which is to find the intensity at 5 meters. So we're finding I at 5 meters. So 5 is d, but we're squaring that. And at this point, all you would do is put that in a calculator. And we should all get that I is equal to 0.324. Normally, we would put units on that, and the units are actually given in the problem. If the problem does not give you units, you don't have to put units on there. But our intensity is watts per square meter. So if I were to write an answer, say in a sentence, I could say the intensity is 0.324 watts per square meter. It's whatever you were given. And that would be solving an inverse variation. We will try this again in example 4. It says the volume of a volume V of a cone varies jointly with the height h of the cone and the square of the radius r of the base. So I'm going to pause for just a second and recall that if we had a cone, so I'm just going to sketch my sad cone, that it's going to have some radius in its base and it's going to have some height. So this is our cone, and the volume V, it varies jointly. So I know that V is going to vary jointly. I have my K. It's going to vary with the height, H, of the cone and the square of the radius, R, of the base. So R squared. I have my equation, and then I'm going to look to see if I can solve for K by the information that they will now give us that says the volume of a cone with a height of 5 inches and a radius of 2 inches is approximately 20.94 inches to the third, so that's cubic inches or inches cubed. So the volume, 20.94, is equal to K. The height here is 5, and the radius is 2, and I'm squaring that. So 5 times 4 is 20. I'm going to get 20.94 over 20 is equal to my K. If we put that in a calculator, I will get 1.047 is equal to K. Now I'm going to rewrite my volume formula. Volume is equal to 1.047. So I'm going to take that K value, I'm going to multiply that by my H and my R squared. The last sentence here will give us the problem that we need to solve. We're supposed to find the volume, so I know I have to find V. I have K of a cone with a height of 3 and a radius of 3. So 3 and then the radius 3 would be squared. I'm just going to put that in a calculator. When I do, and again double check me on this, I get 28.269. The volume is in cubic inches. So if I were to write the sentence answer, I would just write the volume is 28.269 cubic inches or inches cubed. Before we look at our last problem, I would like to go back to the volume of a cone. If you recall from geometry, the volume of a cone has a formula. It's 1/3 pi, and then it's h r squared. Now, our formula that we got was volume equal to K h r squared. So it must be true that 1/3 pi is K. Now, if you put 1/3 pi or pi over 3 into a calculator, you get approximately 1.04719. It's going to go on forever. 75. This is what I got in my calculator, and then it just stopped after a certain amount of digits. But then look at what this 1.047 was. That's that K value that we had when we set up our variation. So these formulas actually are real and they actually do make sense. The last thing we're going to look at is a combination of different variations, which is possible. But remember, you always still just have one K value. It doesn't matter how many variations you combine, always just the one K value. So this is our last example, example 5. We have the resistance R of flow of a blood vessel is directly proportional to the length L of the blood vessel and inversely proportional to the fourth power of the radius R of the blood vessel. So let's just stop there and look at what we have. The resistance R, which is the flow of a blood vessel. So what that's saying is you have your blood vessel, it's a tube. The rate at which, or the resistance that your blood has going through your blood vessel, so resistance would be like slows it down, kind of depends on the length of the blood vessel and the radius of your blood vessel. So clearly, if the radius is really large, the blood can flow faster, so there's less resistance in the flow. As you shrink the radius and you shrink the blood vessel, it slows down the blood flow, so there's more resistance, so R is bigger. And now look at the length of a blood vessel. If it's a short blood vessel, it doesn't take long for the blood to flow through, so there's less resistance. But as you lengthen that blood vessel, it takes longer for the blood to flow through. It slows down, so the resistance is greater. So that's what they're talking about here. So our resistance R, it says that it's directly and is, so equal. It's K, right? Because it's directly proportional to the length L of the blood vessel. So directly proportional means L is going to go in the numerator, but it's inversely proportional. So something's going to go in the denominator, and that would be the fourth power of the radius R. So that's R to the fourth. That's an example of a combination. So we're combining direct variation and inverse variation. Remember, there's still only one K value though. So let's go ahead and look at what's given to us. The rest of the problem, we're not given units, so that means we don't have to worry about units. It says if R is equal to 25, so I'm just going to put 25 for R, solving for K, when L is 12, and R is, little r, is 0.2, so that would be the radius, but remember we're taking it to the fourth power. Find R to the nearest thousandths when L is 10 and R is 0.3. Okay, so we're starting out with a resistance and the units are 25 something. And that's when the length of our blood vessel is 12 and the radius is 0.2. We're going to solve for K, but then look at what we're supposed to find. What we're doing is we're shortening the length of our blood vessel from 12 to 10. So that tells me it's going to decrease the resistance, but we're also increasing the radius from 0.2 to 0.3. So that will also decrease the resistance of blood flow. So I'm thinking that once we figure out what this is, it's going to be less than 25, has to be. Solving for K, I would multiply both sides by the 0.2 to the fourth and then divide by 12. And then when we put this in our calculator, I get 0, 0, 3, 3, 3 forever. Going back to what we're supposed to find R to the nearest thousandths. So thousandths means 3 decimal places. So if you're going to round your K value, you want to go at least one more than what you're supposed to round to. So at least 4 decimal places, just so that when you round your final answer, you can tell if you're supposed to just cut it off or round it up. However, you can also write this as an exact value if you choose to. And I think I'm going to write this as 1 over 300. So all I did in my calculator, I have that decimal fraction key, is I took the answer for K and I hit my decimal fraction key and it switched it to 1 over 300. But regardless, we should all get the same answer. Let's rewrite our equation. So now we have r equal to, I'm going to use the 1 over 300, that's my k value. And then it's going to be multiplied by the length over the radius to the fourth. So length over radius to the 4, my L looks weird, looks like an E. We have to find r to the nearest thousandths when L is 10 and r is 0.3. So 1 over 300 times L is 10, r is 0.3, but we're taking it to the fourth power. You can just put that in a calculator. You can see that you could reduce the 10 and the 300, so it'd be 1 over 30. But I'm just going to put the whole thing in a calculator, and I get r is approximately equal to 4.11522. So you guys double check me on this. So those are all the digits I got in my calculator. For our final answer, we have to round to the nearest thousandth, so that would be tenth, hundredth, thousandth, so it would be to 3 decimal places. If I were to write a sentence answer, it would be the resistance is 4.115. And I don't need to include units because none were given to me. And that's it for this section.